Okay, good morning. This is the second lesson of the course in complex analysis. Last time we have collected some basic ideas on complex numbers, and we were recorded, and I tried to look at the first lesson. It is somehow an unusual lesson, okay? But then I discovered on the internet another colleague of mine who is much smarter than me, so I wanted to show you this video, okay?
Hello there. Nice to see you again. Thank you. All right, go ahead. Okay, I'm going to tell you about complex numbers today. Complex numbers have a real part and an imaginary part.
Correct?
You know what? You're making me nervous. Stand there. Could you just go hide somewhere? Wait, are you talking to me? Yes, you. Just like get out of the way somewhere, because I don't want to see. It makes me nervous. What if I hide in here? Like this? Okay, good. Stay there. Thank you. Okay. As I was saying, complex numbers have an imaginary part and a... Hey, I see you there. Complex numbers have an imaginary part and a real part. I see it's written over there on the whiteboard. If you take a real number plus an imaginary number, then you end up with a complex number. Now, the most important thing about complex numbers is if you take a imaginary number like I... Hey, what's wrong with the connection? That last thing I said was really important. Let me rewind it again so you can see it. So if you take I times I squared, you end up with -1. So
Correct.
that's true for any of the imaginary numbers, because complex numbers are made of... Hey, what is this thing? I don't know what this is, but I don't know why this keeps happening. I'm just going to get rid of this. And so what will happen again, let me move this over all the way to the... There we go. Now it won't... You know what? Wait a second here. Did you start me in Internet Explorer? What were you thinking? You know what? I got to start a better browser here. Let's see here. Okay. Much better. Okay. Now, back to complex numbers. They have the imaginary part and a real part. But you know what? This has gotten me thinking. I'm having a bit of a philosophical crisis here. You know, maybe you really do need a real teacher. I feel like the imaginary part... What? Real teacher? Yeah, you know what? I'm going to have to turn it back over to you. I don't know if I can do this anymore. So, okay. Back to you. Thanks. All right. Well, thanks anyway.
Okay.
Hey, excuse me. Oh, sorry. I didn't mean to be a distraction. Sorry about that. Actually, you know what? Let me just exit out of this, and then we can... All right, that's a good idea.
Okay. Back to business, okay? I want you to use PC today and to give a short introduction to hypercomplex numbers as well. So I will send you the slides electronically. Okay, very short introduction because, well, I think it is worth knowing something about history. So this is something you know, okay? The idea is that quaternions have a real part and 3 imaginary parts with 3 different imaginary units, I, j, k. K actually is I times j. Okay, this is quite known. So the relationships for the imaginary units are given on the right. Sometimes difficult to remember how these relationships are. So it's useful to have this diagram, very simple diagram, I, j, k, and the arrows means that if you are moving on the diagram in the same orientation of the arrows, you are not changing the sign. Otherwise, you are reversing the sign. And well, probably you know this. So I times j is k, ki is j, but if you consider kj is minus I, right? So the first time I heard about quaternions, it was when I was your age, approximately, at CISA, and because there was an important international conference on quaternions. And a Polish guy gave us an introduction to this stuff, and many years later, I started studying also for my own research. But anyway, and when he was introducing the quaternions, he said, you know, there is this story of Hamilton walking along the Grand Channel in Grand Canal, sorry, in Dublin, you know. And he was thinking about the ideas of extended complex numbers, and while walking along the Grand Canal, he had, you know, suddenly the correct idea, but in fact, he tried to extend the multiplication in R3, and he discovered it was possible in R4. Hamilton was an astronomer, an Irish astronomer, quite an intelligent man, very, very well educated. He knew he could speak several languages, he knew a lot of stuff, and he was very smart in calculus. Probably the symbol nabla we normally use in vectorial analysis, tensor analysis, whatever, was invented, well, the symbol itself was introduced by Hamilton. But this story seemed to be kind of legend, you know, for mathematicians. Like, you know, he was walking and thinking about maybe something else, and he discovered something. But then I found out that there is a precise description of what happened in a letter to another colleague. And so there is a precise date when the whole stuff started. It was October 16th, 1858, so quite recently. Okay? Tomorrow will be the 15th birthday of the quaternion. They started into life for light, full ground, blah, 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 on 16th of October, 1843, sorry. As I was walking with the Lady Hamilton, so his wife, and the other part of the legend of the story told us was that he was so happy to have this idea that he couldn't find a place where to write it down. You know, mathematicians need a piece of paper or something like this. And so he went to a stone on the bridge and engraved symbols there. This was part of the legend, I believe. But then, this is another description. When you see very detailed properties of the imaginary units for quaternions. But then I went to Dublin some years ago, and I found on the bridge, on the precise bridge I was looking for, Broom Bridge, this plaque, which commemorates the fact. And every year, apparently, there is a college nearby there. There is a pilgrimage to this bridge just to get the same inspiration, okay? So by the way, in the description, it is also written that he was going to a very boring briefing of colleagues of his faculty, and was thinking something else while walking with his wife. So just to give you an idea how discoveries in mathematicians take place. However, Hamilton was not recognized as an important man when he was alive. He died, he was considered kind of a crazy man. He was not an easy man in the faculty. And only recently, well, this is from the notes of Hamilton, the Irish community started to celebrate this important man. In fact, in Trinity College, if you go there, it is the Hall of Fame, the long room. There are some men, and among them also Hamilton. And this is one of the commemoration, okay? And in the how do you say okay, by the post office. This is another one. So, as I anticipated last time, after the quaternions, there are the octonions. And the octonions have one real part and 7 imaginary parts, okay, octonions. The 7 units, imaginary units, are denoted by I1, I2, I7, and the multiplication could not be right on the right-hand side, not be written, sorry. And I decided to put in a table, which collects the information, but is more difficult than the simple diagram for quaternions. However, this table allows us to consider the quaternion extension of, this table for Kelly numbers, an extension of complex and quaternions. You see, inside there is this copy of C and this copy of the quaternions. Okay, so if you restrict, like for the complex, if you restrict on the real axis, you have the real numbers. Here, if you put 0 to the 6 final components of the octonions, you obtain a copy of C, or if you choose another one, okay? Choose one imaginary unit, one real part, and you have a copy of C, so there. And these are division algebras. Then Hurwitz and Frobenius prove that these are the only ones, as I said. So you have a division algebra when you can find one element which is an inverse on the right, and one element which is an inverse on the left. So as I anticipated last time, these are examples of division algebras, but in, well, see, it's like R2, R is like R. Quaternion is like R4. The product in the quaternion is not commutative, and in the octonion is neither commutative nor associative. And these are the only Frobenius algebras, since the theorem states that this is the only list of algebras. But as you can recognize, okay, the idea of Hamilton is, of course, not a good idea, just to try to extend to R3 or to R5, something which is valid in R2 as a complex number and so on. But every time you double the real dimensional of the structure, so the 1, 2, 4, 8, and in fact, there is a process called Cayley-Dickson construction, which allows you to extend from one algebra to the other, doubling the real dimension. I don't want to enter the details, but after the octonions, there are Sedanions, and then with the 16 components, and then 32 components, so on, as much as you want. This term is, of course, misleading because it's also used for other structures, algebraic structure. However, the Cayley-Dickson process construction produces a sequence of algebras, but these algebras are extension of complex numbers, and they are called hypercomplex numbers. They all have the notion of conjugation and norm, which we already introduced for the complex, which allows you to have a metric structure. Okay? But unfortunately, the octonions are not associative, as I said, and not even commutative. So in the Cayley numbers, you are not allowed to use the associativity of the product, not even the commutativity. Okay? But for octonions, you at least have this property, which is called to be the alternative property for an algebra. So x times xy is xxy, and yxx is yxx. Sedanions do not have this property. They only have the property of power associativity, which is the least condition to define anything which looks like an analytic stuff. Otherwise, you are completely gone, okay? If you don't have power associativity, you cannot write a power series. This notation is, unfortunately, there is also a misprint there, okay? I'm sorry. What is also odd in this construction, that you have zero divisors and Sedanions. And all hypercomplex numbers do have zero divisors, which is somehow difficult to work with. So this is the idea. You get a stop, a theoretical reason that stops you to extend this stuff. And quaternions, you see, are in the center, not by accident, because there is another possibility. There is a possibility given by Clifford algebras. Clifford introduced these algebras for other reasons, but however, quaternions are a good example of Clifford algebra. Quaternions are not, because Clifford algebras are associative. But they do have zero divisors. How can we define very quickly this? So you have a vector space and a quadratic form, Q on it. Then you consider the freest algebra generated with this condition. Okay? The square is this. If the characteristic of the field is not zero, then you obtain this property, which gives you some fact on commutativity. Okay? And there are some simple. This scalar product is the symmetric form associated with the quadratic form. Some examples. Well, if you start from the reals and you consider the relation given by the simple quadratic condition, you obtain CL1 is C, CL2 is the quaternions, but then CL3 is already more difficult stuff, okay? The coefficients are real numbers, and these are E1, E2, and E3 are considered as generators, but we also have E1, E2, E1, E3, E2, E3, and E1, E2, E3, which is called pseudoscalar unit, because this is the property which characterizes the square of each unit is -1, the units. But then the pseudoscalar has a square which is 1. So it's a bit difficult to work with, but in some sense, you have associativity. So Clifford algebras are commonly applied in the study of physics for several reasons. I cannot, of course, explain you now, but they provide good tools to physicists. And this is nothing but a very, very, very introductory presentation of Clifford algebras. Just in case you have heard of this algebras. So I don't want to bother you anymore with this, and I switch to the doccam, if I'm not mistaken. Yes, and I start a normal lesson, say. Okay. So can you hear me even if I sit it? Okay, good. Okay, I wanted to start with some exercises for you. Okay, simple exercises. One is this. So last time we have introduced the polar notation for the complex numbers. We had the argument theta. We associate to theta cos theta plus I sin theta. Okay, so this is a real number, and this is a complex number. And the modulus of this complex number is 1. Okay? So I invite you to verify that this function here called phi gives you homomorphism, group homomorphism between these two sets. Okay, we have the real numbers and the sum. On the right-hand side, I put t. T is, okay, the unit circle. Call it t, okay, but it's up to you, okay? The unit circle. This number here, this complex number has, of course, modulus 1. And the product is the product in C. Okay, I invite you to verify this. So, phi, okay, the exercise is verify. Phi is a group homomorphism. Another exercise I want to leave you is the following. We know that C is a field. Okay? For abstract reasons. But I want you to prove this. Take Z and W equal to 0 times W. Z and W. Pair of complex numbers, and assume that their product is 0. So this implies that either Z is 0 or W is 0. So there are no zero divisors in C. So the characteristic of the field is 0 if you want. Okay? Please do it without using abstract algebra, but making the calculation. Okay? Just to get in touch with the subject. Okay. Okay. This is the list of exercises, and maybe since we have a gap of time from this lesson and the next one, I will send you a list of short exercises during this week. Okay, by email. Okay. Some homeworks for you. All right, so let us continue. So last time, we have considered complex numbers. Like this. Okay? Then I made you, okay, this is, this is a field, and then I made you some observation about this function, I think. I asked you to find an inverse for this number when it is reasonably defined. So I said, well, you can define the inverse. Actually, I asked you to calculate the real and imaginary part, right? But this number, this has a meaning only if Z is different from 0. Okay. Okay? So, I'm sorry. All right. So I have to probably do. So this is a number, is in C, if Z is not 0. Of course, any power of this kind, Z to the minus n, okay, n integer. So the idea is to extend the complex number as we did for the real numbers, and to put two extra or other symbols. Okay, in the case of the real axis, two symbols are added to the real axis, to the real number, plus infinity and minus infinity, so that you have an infimum and a supremum of any set, right? But here, in this setting, we have R2 as the set of numbers we are considering, right? The complex numbers. So it's a bit more complicated to think of adding 1 point, 2 points, several points. How many points do we need? So the idea is, well, in some sense, basic idea is the following. Consider a sphere. Okay, over the plane. this is like R2, that is C. And then I consider what is commonly called the north pole of this sphere, okay? So the equator cuts the plane cuts the sphere on the equator, and then I consider the north pole. So in coordinates, if I introduce Cartesian coordinates in R3, okay? And so the plane, okay, we have 3 components. The third component cannot be Z, because Z is normally the complex number, okay? We use something else. So it's like E1, E2, and E3 are the three vectors in the 3 components. The third component is this one. So we imagine the sphere to be S2. That is to say, the unit sphere centered at the origin of this axis and of radius 1. Therefore, in these coordinates, the point N, I'm considering north pole, has coordinates 0, 0, 1. Okay? So this is the center, so the origin O, and this is the point in the direction of the third axis, not X, not Y. So first, second, third, okay, oriented. Positively oriented, and okay, this is the coordinate. And then any point here, Z, complex number, which I write as X plus IY, has in fact coordinate X, Y, and 0. So the plane, which stands for the complex plane, has equation third component 0. Good. Now what I'm doing is quite a natural thing, is to draw, I'm drawing a line connecting N and Z. And, well, I'll do it here. So I have half sphere here, N, Z, and this is the line, okay? And I consider the intersection of the line with the sphere the other intersection, because of course the line intersects the sphere in N. Okay, so first I write the line. The line is defined as follows, so I consider Tn plus 1 minus Tz. Okay, this is in symbol. So if you agree with me, and T varies in R, we have the entire line connecting N and Z. Why? Because when T is equal to 1, this is 0. And okay, when T is equal to 0, vice versa, this is 0 and this is Z. Okay, this is a line. So if I want to be more precise and use the coordinates, so LT is like this. So I have T times 0, 0, 1 plus 1 minus T X, Y, 0. And therefore, I use these properties of the vector space of R3, and I sum up, and I have this 1 minus tx, 1 minus ty, and t. Okay? So now the question is, what is capital Z? Capital Z is the point on the sphere and on this line, different from M. So t is not 1, okay? When t is not 1, the point LT is not N. But how can I get? Well, which t gives you the point is capital Z? Well, capital Z is obtained by imposing that the point Z is on the unit sphere. So it is to say the first, yes, the sum of the squares, correct, is equal to 1. So the distance from the origin is 0. So Z is obtained for t such that 1 minus t squared x squared plus y minus t squared y squared plus t squared is equal to 1. Okay? Because it is on the sphere. Good. Which is also summarized in this way. 1 minus t squared x squared plus y squared is 1 minus t squared. Putting on the right-hand side t squared. Correct? So as I said, we are not considering the possibility that t is equal to 1. Why t is equal to 1 has to be avoided, because otherwise we obtain n. So if t is not 1, on the right-hand side I have 1 minus t times 1 plus t, and I can cancel. Okay? Okay, good. So I have 1 minus t x squared plus y squared is 1 plus t. Notice that this number here is quite familiar to us. This is the modulus of z. Sorry, modulus square, right. Okay, so probably need an extra piece of paper. Now, some calculations. The relation we have is the following. We have 1 minus t modulus of z squared is 1 plus t. In other words, okay, modulus of z squared is, if you want, 1 plus t over 1 minus t, and I can also obtain t from this, which is what we need to obtain capital Z. And t is, well, quite simply, say t put on the right-hand side, and we have modulus of z squared minus 1 over modulus of z squared plus 1. Correct? So for this t, I have capital Z. So capital Z is this point in R3 is 1 minus modulus of z squared minus 1 over modulus of z squared plus 1 times x. 1 minus modulus of z squared minus 1 over modulus of z squared plus 1 times y, and then the final is modulus of z squared minus 1 over modulus of z squared plus 1, which is t. Okay? So if I simplify this expression here, this is modulus of z squared plus 1 minus modulus of z squared plus 1 over 1 plus modulus of z squared. So it is twice 2 over 1 plus modulus of z squared. Okay? In other words, z is 2x over 1 plus modulus of z squared to y 1 plus modulus of z squared and modulus of z squared minus 1 over modulus of z squared plus 1. Just to complete our calculations, let me observe that this is the real part of z, and this is the imaginary part of the, and we can express both real numbers in terms of z and z bar, right? Okay, so if I want to express z as a function of capital Z as a function of z, I have to write instead of 2x what? Z plus z bar. Because z plus z bar is twice a real part. Okay. Z plus z bar. And y, remember that the imaginary part is given by the difference of z minus z bar over I. Okay? Okay? And finally this. And for the sake of simplicity, we also summarize it, these three numbers like this: u1, u2, and u3. Remember, and you can check it, if we are not mistaken, u1 squared plus u2 squared plus u3 squared is equal to 1. Must be. Oh, well. It's just a check you have to do if you want. Okay, it is the case, right? So vice versa, giving a point on the sphere, u1, u2, u3, such that u1 squared plus u2 squared plus u3 squared is equal to 1. Can we get z on the plane? Of course, yes. What are the relations? Well, from here, okay, maybe I write it on this new. Okay, remember that we had that u1, so the first component of capital Z was 2x over 1 plus modulus of z squared. And u2 was 2y over 1 plus modulus of z squared, right? So that x is what? 1 plus modulus of z squared over 2 times u1, and y is 1 plus u2. Okay? And t was modulus of z squared minus 1 over modulus z squared plus 1, which is u3. Okay? Remember that this number here, 1 plus z squared over 2, was obtained considering what? The reciprocal of 1 minus t. Okay? Okay, and then I have that x is u1 over 1 minus u3, and y is u2 over 1 minus u3, since u3 is t. Therefore, if I have z, capital Z, whose components are u1, u2, and u3, I can pass to the complex number z on the plane, obtained as intersection of the line connecting the north pole to the point capital Z as u1 over 1 minus u3 plus I, u2, 1 minus u3. Okay? So there is a correspondence. Starting from capital Z, I obtain the point on the plane. If starting from a point of the plane, I obtain capital Z on the sphere. Now, what is the next task? Well, to consider on the sphere all the points in correspondence with the points of the plane, except one, the point, the North Pole. Okay? So if you imagine to have a plane like a very large, infinite wrapping paper, we are wrapping the sphere. Correct? So the only point missing is your horizon when you're on the plane. And this stands for the infinity point. Okay? In fact, this process also has some analogous process in topology. It's called one-point compactification. You compactify, okay, the plane, which is open and become closed into a sphere, the Riemann sphere, or extended complex plane. So what is the point at infinity? Well, it's the corresponding point in this construction to the North Pole. Okay? So the model now is not the plane, but the sphere. I want to point out from this construction, you can see that the equator is left fixed by this construction. Any point of radius of modulus 1 is mapping to itself because it is on the sphere already. Okay? And what is inside the unit disk is the lower hemisphere and the outer hemisphere, so the unbounded domain with the boundary, the unit disk, the unit circle, sorry, is the upper hemisphere, including the point at infinity, the symbol infinity, so including the North Pole in the model of the sphere, which means that we are closing it. Okay. Okay. So the symbol we can use is this, which is C. And this point here has no sign, of course. There's no sign because we have no positive, negative symbols, okay? So this is the Riemann sphere, right. And sometimes it is also denoted in this way, okay, in some books, just in case. Okay, this is called the Riemann sphere. And it's obtained, as I said, using that construction, which is also known as stereographic projection, the sphere, and which makes a one-to-one correspondence of each point of the plane with a point of the sphere, except the point North Pole. At the end, it is compact. So it is one-point compactification. Okay? So the next task is, okay, now we have this extended stuff, and so we can use the point at the infinity like a symbol. Like in the case of the real analysis, when you study convergence or limits or whatever, you have to distinguish if sequences, for instance, converge to a real number or not to a real, or is it divergent, okay? And you have to specify. If you use a common language, say in topology, you say this is the neighborhood of infinity, this is the neighborhood of plus infinity, minus infinity. Everything becomes the same in some sense. One point, or okay, has a neighborhood, or which is an open set, small open set, or an affine in there. Okay, the same here, but still, this set has no topology. We haven't introduced any definition of open set, closed set, anything. This is just a set. Okay? And the next task is, well, why not to use some metric properties? We are in R3. Each point of the sphere, okay, a unit sphere, S2 is the symbol for the unit sphere. Okay, I call it S2 from now on. Can be regarded as a point of the extended complex plane or Riemann sphere. And I can use the distance in R3 to define a distance in the Riemann sphere, the standard Euclidean distance, and see what happens. And can I express it in terms of z, z bar, and so on? If I can do it, well, I'd be happy to work with this new distance and introduce then the notions of open set, closed set, and so on and so forth. The only odd part is that we have to make some calculations, and of course, making calculation can be boring and normally can produce some mistakes, okay? So please check what I'm doing. Okay, now I start from this. I have z, as I said, a point in S2, and z prime, whose coordinates are this one, in S2 as well. Then I consider the distance between z, capital Z prime, in R3. And the distance is the Euclidean distance, okay? With this symbol, I say I'm using the Euclidean distance, which is the square root of u1 minus u1 prime squared plus u2 minus u2 prime squared plus u3 minus u3 prime squared. Euclidean distance. Now let us make some calculation, because, well, we have the relation. When I say S2, I mean that u1 squared plus u2 squared plus u3 squared is equal to 1. So this simplifies calculations. And the same is for u1 prime, uj prime, okay? So from this, I have u1 squared plus u2 squared plus u3 squared plus u1 prime squared plus u2 prime squared plus u3 prime squared, which is obtained considering, okay, the squares of the first and the second term in each summand. And then I have the double product of what it, okay? So minus 2 times u1 prime plus u2 prime plus u3 prime. Okay, this is 1 by assumption. This is 1 by assumption. Therefore, the distance we are considering is in fact 2, the square root of 2 minus 2, this u1 prime plus u2 prime plus u3 prime. Correct? Well, this is also familiar to us, or should be. What is this? This is the scalar product of z and z prime in R3. Hence, if I want to summarize the calculation we have done, we have that this distance, say the square of this distance, is 2 minus 2 z bar. I use this notation. Maybe this is scalar product of z prime as vectors in R3. Okay? Inner product. Inner. Yes, scalar product. Sure. I believe this is not misleading. Because, well, it depends. You're right. I agree. Depends on textbooks and the school. In the American tradition, okay, you can put a dot. This, of course, means many things. Okay. What I don't like is to put a cross, which somehow can be used also for the vector product. So I normally use the wedge, and I use this notation, which is somehow redundant, but is also adopted, for instance, by the physicists. They normally use this symbol as an operator, okay, which is represented using the Ritz theorem and so on and so forth. Okay. Not with the simple comma here, but I put a bar here, a line, okay? And I mean this. Okay, it's inner or scalar product, okay? What is left to do? Well, this is nothing, because we don't have these two numbers, okay? This number here and this number here in terms of z. So the next calculation will start from considering this difference and substituting uj and uj prime with the real imaginary part, or the expression with the z bar, z prime bar, and z prime given before. Okay, so I will recall you what we have done. So remember that we have this u1 as 2x over 1 plus modulus of z squared, or z plus z bar. Okay? And u2 is 2y 1 over I z minus z bar. Okay, and then u3 is this. Okay? Of course, similar expression also for u1 prime, u2 prime, and u3 prime. So you have to put a prime, okay, on the right-hand side and on the left-hand side. And similar expressions for uj primes, j from 1 to 3. Now, when I consider the square of the distance, Euclidean distance between z and z prime, I have 2 minus 2 u1 prime plus u2 prime plus u3 prime. And I have to substitute to uj primes this expression in z and see what happens. So I have 2 minus 2, and then I have here, okay, z plus z bar over 1 plus modulus of z squared times z prime plus z prime bar over 1 plus modulus of z prime squared. Correct? Then here, something new. Remember that I have 1 over I in front of this expression. That means that when I multiply u2 and u2 prime, I have 1 over I times 1 over I, so I have a minus. And therefore, this is the expression for this second summand. Sorry. And finally, I have modulus of z squared minus 1 over modulus of z squared plus 1 times modulus of z prime squared minus 1 over modulus z prime squared plus 1, which is the last sum left. All right, so I can also factor out the 2 here. 2. Okay, so I have 2, 1 minus something. And this something has to be calculated, but luckily for us, has the same denominator. Okay, so it is an expression we have to calculate here, something. But the denominator is like this: z squared plus 1 times z prime squared plus 1. Okay? Are the same, and here are the same. Okay. Now, you probably better have on your notes everything written like up to here, okay? Because I have to change. I keep it here as a copy for me because it's not easy to remember. Anyhow, I continue here. 2 times 1 minus, so the expression is very long, but the denominator is good. So remember we had z plus z bar times z prime plus z prime bar, which means z prime plus z prime bar plus z bar z prime plus z bar z prime bar. Okay? Then I have a minus. This minus was given by I times I. So minus here, and I have to multiply the difference z minus z bar times z prime bar. So I have minus z prime plus z prime bar, then plus z bar z prime, and then minus z bar prime. And I continue here. Okay, minus.
Not plus, it's minus.
Sure. Yes, correct. I put plus here and minus here, right. Sorry. Yes, it was a minus in front of the entire fraction, correct. So some part should cancel. So I think this and this should be cancelled, and this and this. Okay? Okay, so finally I have 2, and I put on the same, so this is a 1, okay? So I multiply everything times this. I have the same denominator. And what is left here is the following: minus z prime bar minus z bar z prime, Then I have minus z prime bar minus z bar z prime, and then also again plus, here is a minus I have what? I have correct modulus of z squared, modulus of z prime squared, minus modulus of z squared minus modulus z prime squared plus 1. And here, notice that then I have 1 here and minus 1 here, z and z prime modulus of z squared plus modulus z prime squared, which cancel this. So the final expression after some efforts should be is this, okay? Modulus of z squared plus modulus of z prime squared minus z prime bar minus z bar z prime minus z prime. Yes, correct. You can summarize this and this, right? Because when I consider this square of the modulus z times z prime square, this is cancelled by this because we have a minus in front. 1 is cancelled by minus 1 here. And then I have a minus here, which gives you 2 times the modulus of z squared given from this times this and this times this, okay? So at the end of the day, we have a 4 in front because we can factor out again 2 denominator, which is the same as before. And here I write instead of z. Sorry? Sorry. Yes, sure. Second, yeah, sure. I want to write this in this way, okay? And I'm allowed to do this. Then I have plus z prime bar, similarly. And then I have minus z prime bar minus z bar z prime. And hence, if I make the right considerations, this is z minus z prime times z bar minus z prime bar. I have z bar minus z prime bar. Then I have z prime, z bar, the minus in front, then plus z prime bar. And this is the conjugate of this. I also write the denominator. So that the final expression is the distance, the square of the distance between z and z prime is 4 times z minus z prime squared over 1 plus modulo z squared So the distance is, in fact, times over the square root of this number This distance is valid for any pair of points on the sphere, and relates the distance with the standard distance, the distance of 2 points on the plane. This is the distance of 2 points on the plane, and this is the fact. But for consideration about convergence, so what is important is to control this and not to control this. This can be large, but it's not a problem, okay? Because it's a denominator of positive numbers. There is one point missing. In our transformations, we applied the formulae obtained before, but if you remember, we assume that t is different from 0. T different from 1, because we are not considering the point n. So there is one point missing. So this is the distance for any pair of points different from the North Pole. So what is the distance of a generic point, see, from n? N is the North Pole. Well, let us do the calculation. Z as coordinates u1, u2, u3, and n as coordinates 0, 0, 1. So take the square, as usual. I have u1 squared plus u2 squared plus 1 minus u3 squared, which is simply u1 squared plus u2 squared plus 1 minus 2u3 plus u3 squared. Yes, please.
Z is in sphere 2.
Okay. Z is in S2.
What is Z is 1?
The modulus of Z is equal to 1. That's what I assumed from the very beginning. The capital.
But in distance of.
The distance is in the sense of Euclidean distance from the origin. So you define S2 to be the unit sphere in R3. So a point on a sphere, S2, is a point whose distance from the origin in the sense of Euclidean distance in R3 is 1. So I'm assuming here that u1 squared plus u2 squared plus u3 squared, and I'm going to use it, is equal to 1. So that this expression here, if I'm answering you, is one given by this 3 summands plus 1, 2 minus 2u3. Okay? But remember that u3 was t, or modulus of z squared minus 1 over modulus of z squared plus 1. And once again, we have that this is 1 minus u3, or 2 times modulus of z squared plus 1 minus modulus of z squared plus 1 over 1 plus modulus of z squared. This cancels this, and the final result sorry, I'm running out the paper. This is the expression for the distance in the case Zn. The pair Zn is the square of the distance 4 over 1 plus modulus squared. And the distance, therefore, is the distance is 2 over square root 2. Which agrees with our idea that when z is very far from the origin, this number becomes very small. Okay? So now we have a distance remember the construction, this projection, this stereographic projections allows you to consider what? Something which is on the sphere, something which is on the plane in correspondence. And the distance is related like this, okay? You take this as a distance between the two corresponding points in the plane, if you want, in the extended plane, okay? Good. We have a metric structure on the Riemann sphere. We have a way to say if a point has a certain distance from another. We can start, constructing objects like conditions, or say, set of points which has a certain distance from another point, and so on and so on. But also, we can introduce the corresponding topology, the metric topology, which is natural to use. And as we discovered that the distance, remember the distance of 2 points in the model of the sphere is related to the distance of the 2 points in the plane. The 2 points are very close, this number becomes small. In this sense or in this sense. Okay, so what I want to say is that we can now introduce in C hat in the Riemann sphere the induced topology. And then we have the notion of open sets, closed sets, connected sets, compact sets, okay? All this stuff is induced by the topology, the metric topology. When we have a topology, then we can start thinking about limits, convergence of points, of elements of the plane or of the sphere using this topology and in some sense also the distance. There is one important point when you are working in a metric space. Is this space complete or not? Because this helps us a lot in case we need. So the real numbers with the Euclidean topology, so the topology induced by the Euclidean distance, is a complete space. This is one of the important facts you should know, okay, about the real numbers. What about the complex numbers? I don't want to leave you like an exercise to prove this, but it should be an exercise actually. Because the question now is C a complete metric space? Yes. Okay. How do you prove this? Somehow component-wise. Very good. So first of all, okay. What do we mean by complete metric space? Please tell me. Okay. Any Cauchy sequence is convergent. And, well, assume that we have a Cauchy sequence of points. how can you express that this is a Cauchy sequence using the distance we have so far introduced? Okay, in the usual standard way. So forget that we are working with the complex numbers. The notation is very similar. For any epsilon greater than, okay, positive, there exists n such that for any n, m, okay, we have the distance between Zn and Zm is smaller than epsilon. The distance, okay? I'm saying the distance, but well. What do we know about? Exactly. What do we know about exactly the real part of Zn? Well, the real part of Zn and the imaginary part of Zn. Exactly. And this should be enough, because what do we have? We have in particular, the real part of Zn minus Zm smaller okay, so component-wise, as suggested by our friend, you obtain that the real part is a sequence of, it's a Cauchy sequence in the real numbers. So it is then convergent. I is a constant in some sense, because when you consider the modulus, i's disappear. From metric point of view, if you are at the same distance from the origin, the fact that you have a different argument doesn't change very much. Okay? For metric reasons, if you are on the, say, a certain distance r, and your argument varies from 0 to 2 pi, for metric reasons, this is unimportant. Okay? So this is one case in which the information on the real is very important for the complex. Okay? So we obtain two sequences, the real part, the sequences of real parts and the sequences of imaginary parts. They both are Cauchy sequences. They are convergent, and they converge to a point, and the real part and the imaginary part of they are, in fact, the real part and imaginary part of the convergent, of this, of the limit of this sequence. Good. Okay, but I didn't repeat what we mean by saying that a sequence has a limit. Well, it has a finite limit if it gets closer to the value of the limit, definitely from a certain n to infinity. Okay, so Zn tends to Z naught in C if Zn minus Z naught is smaller than epsilon, any positive real number for any n greater than n naught, okay, for the distance. And this, of course, reproduces the same or similar condition also in the sphere. Because if this is controlled, then whatever happens to the modulus of Z, this controls also the distance and in the sphere. Well, now, since we know that C is a complete metric space, we can also rephrase it, because this is equivalent to say, well, Zn is a Cauchy sequence. So, okay, if you have a convergent sequence, then necessarily it is Cauchy. But if you have a Cauchy sequence, then not necessarily, only if the space is complete. Now we have this, when we can rephrase it, and it will be useful to know that the space is. So this, in the case of, is the same to say to this for any n and m greater than a certain n. Because, now let us introduce the new topic. Starting from a sequence of numbers with some algebraic properties, like the complex numbers, when you have a sum, you can also consider the sequence of partial sums. This is to say, z1 plus zn. And now the question is, when does the sequence Sn associated to the sequence Zn converges?
What?
When, how, and why should converge? This is a sequence of numbers. Huh? This is an element in C. Well, it is convergent if and only if okay, there exists a certain n such that okay.
You can say modulus Zn, okay. If n is greater than n, okay, we can say, okay, modulus Zn plus 1 plus Zn plus 2 plus Zn plus 2, okay, and so on to Zn smaller than epsilon.
Well, this is an equivalent way to say that this new sequence I obtain is a Cauchy sequence, and we have just seen that this implies that the sequence is then convergent. But if you look at the construction of Sn starting from a sequence Zn, you obtain that this is in fact the summand up to a certain n, then a summand up to a certain m is cancelled. So you have in between n and m. It depends on what is greater than the other. Okay, but you have okay. This is an equivalent way. So I think we better start talking about this kind of problems next time. But the idea is to find conditions to have information about convergence of series. Series means the infinite sum of complex numbers. Okay? So if the limit exists of Sn, as n tends to infinity, what we find is the series of complex numbers obtained in this way. And we can have several examples of complex series, and the important notion we have to introduce using geometric properties characterize those sets of points, changing the variables Cj's involved in the sum, which guarantees that the series is convergent, because otherwise it is divergent. Okay? Why we are considering series? Well, and not starting with something else in analysis. You see, this is apparently a strange way to introduce functions nowadays. We normally study functions between two sets using the standard, very abstract idea of a law. Okay, each point of the domain is associated to one and only one point of another set, and so on and so forth. But this is quite a recent way of introducing functions. They're quite modern. At the time of Gauss, Euler, and so on, nobody could even think of a law, of an arrow between sets. They had only the possibility to calculate values of a function without knowing exactly what they was doing. They could calculate. They had something real, okay, concrete, more precisely. And they were very smart in calculations, very much smarter than I am, of course. And it is somehow also in our modern computers, when they have the calculation done quite fastly, but essentially they are very simple calculations. What are simple calculations? Well, calculation that can be reproduced in terms of sum and products. So, for instance, in the complex numbers theory, functions were essentially polynomial or extension of polynomial functions. The functions known in complex analysis at the very beginning were power expansions of what we call it power expansion of functions. Okay, now it's vice versa. The idea is completely reverse. The point is that the theory of complex valued functions, in fact, was called also in the German tradition function theory. You find many books, textbooks also with this name. Complex analysis is a very recent way of introducing this stuff. So the good point of view is that starting from series, you can see that these are the proper functions in the setting of complex valued functions. And we'll see that what are interesting from the point of view of the analysis are in fact analytic functions, complex analytic functions. So the two definitions agree, okay? But we have to be to get some other extra information about the convergence of series, of complex series, to better understand complex functions. Okay? So I think that I stop here, and I see you next Friday. Okay?